Last time we started to talk about a very important component that is usually that is part of the sequential circuits, which is the storage elements, which is basically, we said a storage element is a logic circuit that is designed to store one bit as long as the power is available. And usually this storage element has inputs and has outputs. The inputs are basically used to control how to control the stored value. While the output is basically the stored value. So here we have the output Q, which is the stored value, which is the observed value, which is the value that we can see as the stored value. And usually we said the storage elements, they come with a complementary output, which is the complement of the stored value, because as we will see later when we talk about the design of sequential circuits, sometimes when you design the sequential circuit, you need to use the complement of the stored value, not the stored value. So instead of bringing an external inverter or NOT gate, you can use this complementary output. So in the commercial storage elements, usually you will find that every storage element has Q and Q bar, or has the stored value, gives you the stored value and the complement of the stored value. So we said basically there are 4 types of operations that can be supported by different types of storage elements, which are set, reset, hold, and toggle. And some storage elements, they have all of these operations. Some of them, they have subset of these operations. We said storage elements, there are 3 different categories of storage elements: the latches, the clocked or controlled latches, and the flip-flops. Last time we talked about latches, and we had an example, which is the SR latch. We said this is the circuit of the SR latch, which is capable of storing 1 bit Q and its complement, and it can be controlled using 2 inputs, the set input and the reset input. And we analyzed this circuit in details, and it is animated. You can go through it but on your own if you did not get the idea last time. So basically this is the summary for the SR latch. This is the block diagram that we are concerned with. Usually we work with this block diagram, but we should know what is meant by SR, Q, and Q bar. And this is the table that tells us how this latch behaves, or how this latch works. So basically 0, 0 on S and R implies that the new value that will appear, that will be stored, is basically the old value, which is no change or hold operation. 0, 1 implies reset. 1, 0 implies set. And we said 1, 1 is not valid input, is not an allowed input. So we should avoid it whenever we use the SR latch. So this was what we discussed last time. And we also introduced the concept of the timing diagram, which is basically a diagram that investigates the behavior of our circuit. It is not necessarily a storage element or a sequential circuit. It could be a combination and logic circuit. So the timing diagram is used usually to show the behavior of the circuit over time if we change the inputs. So here we change S and R from 0 to 1 to 0 to 1 to 0 and so on. Same thing for R. So we observed what happens to Q. And since we know what is the relation between S and R and Q, we can determine what is the new value for Q whenever we change the inputs. Okay, so this is very important concept, the timing diagram. It can be used with combinational circuits, no problem. We can have the inputs and the outputs. We monitor the output as we change the input. But we introduced this concept here in the chapter 5. We also talked about another example, which is the S bar, R bar latch. It is the same, essentially the same, except the fact that the S and R inputs are active low inputs. In other words, they have effect on the stored value when their value, when they are 0, not 1. So the table that describes the operation is basically the complement of the table we had for the SR latch. Okay, so if we look at these latches or this type of storage elements, which is the latches, we see that if I go back to this timing diagram, we see that as soon as either S or R change, the stored value is allowed to change as soon as the input changes. As soon as the input it changes. So we said that there is no control. There is no control for the user to decide when to allow the change in the input to affect the stored value. So this is basically makes it difficult to analyze and design sequential circuits. If the stored value is allowed to change at any instant of time, then if you want to design a circuit that behaves in a certain manner, that changes the stored value and outputs in a certain manner at specific or during some times, then this makes it difficult to design the circuit, because if the stored value is allowed to change whenever the input changes, then you need to monitor the input at every time, at every instant of time, in order to decide whether there is a change in the stored value or not. So this is very difficult because you need to monitor the circuit and the input all the time. So you need to keep your eyes open and look at the input at any instant of time. So this is difficult because you need to stay awake all the time. So that's why we can make it easier for ourselves if we allow the stored value to change during a specific instant or during some period of time only. In other words, we want to control when the stored value is affected by any change that happens at the input. So basically, how can we do that? We can add another input to control when the inputs can affect the stored value. Instead of allowing the inputs to affect the stored value at any instant of time, we can limit the operation of the latch such that it can allow the input to affect the stored value during some period of time. And to achieve this, we need additional input, which we call the control, or we call it the enable, we call it the clock, whatever you want to call it. So we will add an additional input to control when the input is allowed to affect the stored value. So if we do that, we will have a new type of storage elements, which are called the controlled or the clocked latches. So if you hear the term clocked latch, so at the end of the day, you are talking about a storage element that behaves has inputs, has outputs. The input and the output that have some predetermined behavior. However, you can control when the input is allowed to affect the stored value. In other words, you can enable the inputs to affect the stored value. And one example on such type of storage elements, which are the clocked or controlled latches, is the controlled or clocked SR latch. So essentially, it is an SR latch that we discussed last time. This is the SR latch that we discussed last time, which is a cross-coupled NOR gates. We have S, we have R, okay? However, we added a new input, which is C here, which stands for control, stands for clock. It is enable. And what is the purpose of this additional input is basically to control when these inputs are allowed to affect the value that is stored in this latch. So basically what we did here, this input is it controls whether R and S have effect. So how to do that? Basically we added these two AND gates. And if you remember, these two AND gates are basically enabling circuits. So let's try to look here. If the clock is 0 or C is 0, 0 and R, we will have here always 0. 0 and S So this will be always 0. So whenever you have 0, 0 at the input of an SR latch, what is the relation between Q, the old Q and the new Q, the old stored value and the new stored value? 0, 0 on SR latch, no change, right? Hold. So whenever, as long as the clock is 0, the actual inputs to the SR latch is 0, 0. And 0, 0 on the SR latch implies that the new Q will be the same as the old Q. So whatever happens on S and R is masked, is canceled by this control or by the clock. So it's very straightforward. In order to prevent S and R to affect the stored value during some time, we added this external input, which is the control or the clock, such that when the clock is 0, the actual R and S that are fed into the SR are always 0. Whether R is 1 or 0, whether S is 1 or 0, if C is 0 or the clock is 0, we always have this latch operating in the hold or no change state. So this is what we have, or let's, before looking at this, what if now, if the clock is 1? Now, if the clock is 1, what will happen? 1 and R is R, 1 and S is S. So whatever value is R is passed through, whatever is the value of S, it is passed through, and the latch is operating normally depending on the values of S and R that are passed through the AND gates in this way. So basically, this is the summary. As long as C is 0 or the control is 0, regardless of S and R, we don't care about the value of this S and R, because this implies that the actual S and R that are going into the SR latch are 0, 0. So this implies that no change, there is no change. However, when the clock or the control is set to 1, the latch is operating normally. 0, 0 implies no change, 0, 1 implies reset, 1, 0 implies set, and 1, 1 is invalid state. So this is basically the idea of clocked latches. As we said, we have a latch, the normal latch, which is the first type of storage elements. And we added just a control input to control whether the external inputs that control the operation of the clocked latch are allowed to pass through and affect the stored value. Okay, so this is the block diagram of the clocked SR latch, where we have the set input, the R input, the Q bar, nothing new, but now we have additional input, which is the C input, which controls when S and R affect the stored value. So as long as, in this case, as long as C is 1, as we said, this is normal operation. If the latch is operating normally, C is 0, the latch is in no change state or is disabled, let's say, which means that the input has no effect on the output. This is the same that we did in the decoders. If you remember, we added the enable, and whenever the enable was deactivated, the output of the decoder was not affected by any change in the input. Okay, so you need to be familiar with the block diagram of the clocked SR latch and this table, and the basic simple understanding of this table. So let's look at an example here. We have an SR latch. So we have two inputs, SR and control, now a clocked SR latch, and the stored value. And we want to change SCR in certain, to follow a certain pattern and see how does this affect the stored value. So what we have here is the clock, which is changing in like this. So now here it is 0, here it is 1, and here it is 0. So during this time, this is time, uh, S and R changed like this, as given. We want to see what is the effect on Q. And this is very straightforward. If you look at the timing diagram that we have in the SR latch, in order to decide what is the value of Q at any instant of time, we needed to monitor R and S, and we needed to see what if there is any change in S and R for every time, for every instant of time. However, here it is a little bit easier because it is a clocked latch. So we need to know, or we need to monitor S and R only if the clock is 1, because this is the control. So regardless what happens for S and R, when the clock is 0, we don't care about S and R. So as long as the clock is 0, which is here, any change in S and R will not affect Q. So if Q is initially 0, it will stay 0 as long as the clock is this, or the S and R are disabled. In other words, C is 0, because we have no change. However, when the clock becomes 1 here, we need to open our eyes and monitor S and R and see if there is any change in S and R during this period. As long as the clock is 1, then this implies we will need to monitor S and R, the changes in S and R, and reflect them on the Q. So what we have here we have S is 1, which means, and R is 0 during this period, which means that it is a set operation. This is 1 and this is 0, so it is a set operation. So what will be the effect on Q starting this time? It will go to 1, which means set operation. Afterwards, S becomes 0, R is 0, 0, 0, 0, 0 on SR latch implies a hold operation, so the Q stays the same. Then here R becomes 1, and this is the S is 0, 1, 0 implies reset, so Q goes to 0. Then we have 0, 0 here, which implies hold, so the Q is 0, so it stays 0. Up to this point, any change in S and R has to be reflected on Q. Now, when the clock or the control goes to 0, no change, any change in S and R will not affect Q. So that's why here we have no change. So the Q was originally, before this instant of time, the Q was 0, so it will stay 0 as long as the clock is disabled. Okay, so basically this is easier to analyze because the only time that we only need to look at S and R, or the control, these inputs, only when the clock is high, Otherwise, during this period of time and this period of time, the Q will not change. Even if S and R change millions of times, they will not affect the stored value. So as you see, this is much easier to work with because we only need to look at S and R during this time only. This time might be this long, might be shorter, might be longer. We don't care. The most important thing is the idea. If the clock is 1, we need to look at S and R and reflect the change, any change on them on Q. Otherwise, as long as the Q or the clock is 0, nothing happens to the stored value. Whether it is 0 or 1, the stored value stays the same. So this is easier to work with. You don't need to monitor all, I'm sorry, you don't need to monitor this the whole time. You only looked at this time only. Right? Any question? You need to understand this. It's very simple, but you need to understand it in order, as I said, if you understand the storage element, the concept of sequential circuits, you are done with this chapter. What is left is basically using chapter 3 to design sequential circuits. The same tools, which is key maps, simplification, and all that stuff. So another example on the controlled latches is the D latch, which is basically, I don't want to go into the details, which is basically a controlled SR latch. It is a controlled SR latch. So here we have S, we have R here, but the D latch basically connects these two inputs, which are the S and R, to one input, which is called D. And why is this done? Basically to get rid of the invalid state. So if you connect D, this single input, here it is S, and here you take the complement of it and assume this is R, then S and R will never be the same. So either you have 0 or 1. You can change the stored value to 0, or you can change the stored value to 1. So the basic idea of the D latch is to avoid, it is designed to eliminate the invalid state or the invalid combination, which is when S and R are both ones or are both zeros. This is, if you remember, this is an S bar, R bar latch. Okay, we added enabling circuit using NAND gates, and at the same time we connected the S input and the R input to the same input. So S and R can never be the same because there is an inverter here. So S and R can never be 1, 1, which is the invalid state. And of course, we have the clock or the control, which allows or which decides when D can change Q. So if we look here at the table, as long as the clock is 0, the old value is the same as the new value, or it is just the opposite. The new value will be the same as the old value. Now, when the clock is 1, the new value is basically D. And this is very simple latch. It is very simple storage element. We say that the new value is always the same as D when the latch is enabled. Or they say a Q of T plus 1 follows D. So Q of T plus 1 is the same as D as long as the clock is enabled. So the block, if we look at the timing diagram of an example on the timing of this latch. So let's say that the clock is something like this, which is now, in this case, it is a periodic square wave. It repeats, okay? But it doesn't have to be this way. It doesn't have to be periodic. But in this example, it is periodic. So if the clock is like this, and the D is changing like this, can you tell what is the effect of these two inputs on the stored value, assuming that Q is initially 0, or the stored value is initially 0? What will happen? Since this is a clocked latch, and effectively it is it is enabled when the clock is 1, we only need to look at D when the clock is 1. So we need to look during these periods of time only. During these times, the D is allowed to affect Q. And essentially, how does D affect Q? Basically, the Q is basically D, or Q follows D. Q is the same as D. So what will happen to Q if it is initially, oops, yeah, what will happen to Q if it is initially 0? As I said, as long as the clock is 0, not any change in D will not affect the Q. So if we look here, Q stays the same, which is initially 0. So it was initially 0 here. And since the clock is 0, any change on D will not affect the Q. If we move forward, during this period of time, the clock is enabled. So whatever happens on D will affect Q. And the way it affects this, it affects Q is basically Q becomes D, or Q follows D. Now now during this period of time, the clock is disabled, so any change on D will not affect Q, so that's why Q stayed the same. There is no change. And the same thing here. Q will stay the same until we have this clock set to 1, and this moment Q will follows D, and here D changed, but it did not affect the Q because the clock is disabled. So basically, this is the summary. As long as the clock is 1, then the output is allowed to change, or the output may change depending on the change in the D input. So it will affect the Q, as we said. Another example, I guess here, it is straightforward. If the clock is like this and D is changing like this, what will be the Q? Basically, as long in this period of time, the Q will stay the same. During the red period here, Q will follow D, and here Q is not affected by any change in D. So if we look at how this is going to happen, it is like this. So in this period, the output, or the stored value in this case, which is the same, is allowed to change, However, the changes that occurred here, for example, for D, did not affect Q. Q stayed the same because the clock is disabled. So in order to analyze a circuit that contains this type of storage element, which is the D latch, which is a clocked latch effectively, that is constructed from an S bar, R bar latch, such that there is no invalid state, as we see here. Basically, we need to analyze the circuit only when the clock is enabled, only. Now, the block diagram of this storage element, which is the clocked latch, is like this. We have two inputs, the D input, which specifies what is the Q value when the clock is enabled. Okay? Any question? So now we have clocked latches, two examples, clocked SR latch and the D latch, which is essentially a clocked latch. Any question? Okay. Now, this latch and the previous one, which is the clocked SR latch, are called pulse or level triggered storage elements. What do we mean by level triggered storage elements? It means that these storage elements are enabled based on the level of the clock. In this case, it is positive pulse. We say this is positive pulse triggered latch, which means the latch is triggered or enabled when the pulse is positive. Now, in some cases, the latch might be designed such that it is enabled when the clock is 0, or C is 0, or we say the latch is negative pulse triggered or low level triggered. Negative pulse or low level trigger. And in that case, you will find a bubble on the clock. So if there is a bubble here, then the latch is basically enabled when the clock is 0. If there is no bubble, then this implies that the latch is positive pulse triggered, or when the level of the clock is basically high or positive or 1. Okay, so please remember this. The clocked latches we call them level triggered. We call them level triggered storage element. They are enabled based on the value of the clock, whether it is 1 or whether it is 0. So for positive pulse triggered, we have the latch enabled when the clock is at high level, or it is positive level, or positive, we say positive pulse triggered. For other latches, if they are negative, this implies that the latch is enabled when the clock is 0. So in general, we say that the controlled latches are level triggered. They are enabled when the clock has certain level, whether it is the high level or it is the low level. That's why we have positive pulse or positive level and negative level. Negative level. Okay, now what was the advantage of the clocked latches? Basically, they enabled us to restrict our attention to some period of time. Instead of monitoring the inputs for the whole time, we are now capable of reducing our effort so that we can only, or we need only to monitor the storage element during some time only. We don't have to monitor the whole time. And and why did we design such storage elements? Because we want to make our life easier. We want to monitor the stored value during some time. We don't want to monitor the stored value for the whole time. However, if you look carefully on the clocked latches, as long as the clock is enabled, we need to monitor the inputs and see how they affect the output. So let's assume that the clock stayed on or high for a very long period of time. Then we need to monitor the inputs for the whole period of time. So can we make things more can we make things easier to work with in terms of storage element and monitoring effort? What is the next level? The next level is basically to design a storage element that is allowed to change the stored value at, this is very important, at specific instant of time. So in order to use this storage element, we don't need to monitor the inputs for the whole time. We don't need to monitor the inputs during some period of time. We only need to monitor the storage element at specific instant of time. So if I tell you that this storage element is allowed to change the stored value at 12 o'clock only, do you need or do you care what happens at the inputs at other times? Of course not. You just watch your clock, and when 12 o'clock comes, you look at the inputs and take their values and reflect them on the stored value. This is much easier than working with a clocked latch, which is allowed to change its stored value, let's say from 12 o'clock to 4 o'clock. So if I tell you have a storage element in which the stored value is allowed to change from 12 o'clock to 4 o'clock, based on any change in the input, then you need to monitor the inputs for 4 hours, from 12 o'clock to 4 o'clock. The situation is even worse when you look at the latches. The latches, they can change their stored value during the whole day, at any time during the whole day. So you need to stay awake for the whole day. So your life becomes easier if you have a storage element that you know it is allowed to change its stored value at a certain time. So you only need to open your eyes at that instant of time, read the inputs and reflect them on the stored value. So this is basically the third type of storage elements, which are the flip-flops. We call them the flip-flops. Basically, they are storage elements. Any flip-flop is a storage element that is capable of storing 1 bit. It has inputs that affect the stored value. And at the same time, it has an input that decides what instant of time is used to allow the inputs to affect the stored value. So these flip-flops, basically storage elements that are enabled, let's say, at specific instant of time. Okay, the latches were at any time. The clocked latches were during some time, while the flip-flops, they basically they are basically enabled at specific instant of time. So flip-flops, we say that flip-flops are edge-triggered elements. Basically, as we said, we are working with digital systems. So the values for any variable in our system is basically 0 and 1, 0 or 1. So if we want to define some instant of time, given the fact that we have only two values, what is this instant of time? It is basically a transition from 0 to 1 or a transition from 1 to 0. So the flip-flops are designed usually such that if the clock or the control changes from 0 to 1, then at that instant of time, the inputs are allowed to affect the stored value. Or the flip-flop can be designed such that if the clock is moving from 1 to 0 or from high to low, or it is falling from high to low, then the inputs are allowed to affect the stored value. So in order to define this specific instant of time, which is the at, in digital systems, basically we have to monitor either the transition from low to high, which is called the positive edge or the rising edge, or we monitor this instant of time, which is basically called the negative edge or the falling edge, the transition from high to low. So the flip-flops are designed either to work at the positive edge, to be enabled at the positive edge, or to be enabled to work at the negative edge. That's why we call the flip-flops, we say the flip-flops are edge triggered, or they are edge activated, let's say. Trigger implies activation. So it is edge activation. So the flip-flop is activated at the edge, either rising edge or positive edge or negative edge, which is just which is different than the clocked latches, where it is level triggered, level activated, either at the high level or the low level, at the positive pulse or at the negative pulse. So if you look here, we can define this instant, specific instant of time, either by this or by this. Okay. So how to build these flip-flops such that they are only activated or triggered at the edge? There are many ways to do that. One way is to use the master-slave approach, to design a flip-flop. And what we have here is a D flip-flop. We call this a D flip-flop. And basically it is constructed using two D latches. This is a D latch and this is a D latch. It is straightforward. And there is one D, because it is a D flip-flop, so there is D input, which is the data, okay? And this is the stored value. This is the value that we can see, that we are going to control. So if I want to change the stored value to 0, I will place 0 here. If I want to change the stored value to 1, I need to store 1 here, because this is how the D latches work. Q follows D. If you want to make a Q 1, you make D 0, you make D 1. If you want to have Q 0, you force D to be 0. So how does this circuit basically work such that Q is only allowed to change based on the value of D when the clock changes from high to low, or from at the falling edge. Let's try to analyze this circuit. If you look here, the two latches that we have are clocked by the same clock. However, one of the latches have the clock connected directly to the external clock, and the other latch has its clock input connected to the complement of that clock. So what does this mean? When the clock is 0, the first latch is disabled, the second latch is enabled, right? Because 0 complement 1. So this is enabled and this is disabled. And when the clock is 1, this latch is enabled and this latch is disabled because we have here 0. So these two latches, they work in tandem, we say. One of them is enabled only at any instant of time, either the first one or the second one. The first one, we usually call it the master. The second one, we call it the slave. And I will tell you why they are called this way. So what happens now when the clock is 0, which is what we have here in this timing diagram? Clock is 0 implies this latch, the master latch, is disabled. So whatever happens on D will not change the intermediate Q that we have here. Okay, so this value will be fixed, which is the Q for the master. As long as the clock is 0, the Q master will be fixed because the latch is disabled. However, this latch will be, the slave latch will be enabled. So whatever is Q here, which is fixed, will appear on this Q, because Q slave will be the same as the Q master. So this is what we have here. As long as the clock is 0, whatever happens on D will not affect the Q master. That's why the slave clock, or the Q for the slave, or the stored value on the slave, is not affected by any change in the clock. Okay. So now when the clock becomes 1, this implies that the master latch is enabled and the slave latch is disabled. So only the Q master will change while the Q slave will stay unaffected. So during this period of time, only the master Q will change while the slave Q is not affected. Now, when the clock switches back to 0, the master Q will stay the same. It will not be affected by this, while the Q slave will change to follow this, to follow the master Q, because this will pass through to the slave. So if we look here, the changes that we are having external outside this block, assume this is inside a block, so we only have control over D, clock, and this Q. So assume this is in a block. We don't see the Q master. We have control on D, clock, and the Q. So now, if we look at the timing diagram below, in terms of the relation between clock, D, and the Q slave, we see that regardless of the changes that occurred in this time and the changes that occurred in this time, during this time, for D, the slave, the Q slave, or the stored value that we are observing actually, that we are concerned of, only changed at where? At this edge, at this instant of time, which is at the falling edge, at the falling edge. So effectively, it looks like if we only forced Q to be affected by D only at the falling edge, only at the falling edge. Okay, so this is very important. This is one way to build a D flip-flop, which is a storage element that allows the stored value to change based on the input when the clock changes from high to low or from low to high, or when there is a positive edge or a negative edge only. In this example, the stored value, which is in our case this, the slave clock, is only, the stored value is only allowed to change at this edge. It looks like it is a negative edge triggered. So we took this D value at this instant of time and reflected on Q, I'm sorry, and reflected on the Q. So this approach of building flip-flops is basically called master-slave, because we have two latches. One is called the master, one is called the slave. And why is this called the master? Because basically it is the latch that controls the value that appears at the falling edge in this example. Because The last value that we have for the master is basically the value that we will propagate or that we will give to the slave. So the value that appear here is a slave for the value that is here at this instant of time. That's why one is called the master. It is the master that controls the value that we see at the output. Okay, any question? This is very important, but at the same time, as I said, it's kind of easy if you follow with me, if you know what is the difference between the three types of storage elements. And as I said last time, we are going to work only with the flip-flops, which are basically storage elements that change the value at specific instant of time when we analyze and design sequential circuits. But in order to know how flip-flops work, in order to be able to build flip-flops, we needed to go through all the other storage elements, the latches and the clocked latches. Another way to build the flip-flops is this approach, but I will not go into details. It is kind of, it will take a long time for us to analyze this circuit to prove that this circuit is basically a positive edge-triggered flip-flop, D flip-flop. And this is the graphical symbol, the logic symbol for the D flip-flop, which we have here. This triangle implies this is the clock input, and it implies that this is an edge-triggered flip-flop. And it is, technically, it is a positive edge-triggered flip-flop, which implies that D only affects a Q at the rising edge, The flip-flop might be negative edge-triggered, which implies it D affects Q at the falling edge only. And this is illustrated by having a bubble here. As we said earlier, for the clocked latches, we may have positive pulse triggered or negative pulse triggered if there is a bubble at the clock input. So whenever we see a triangle here, an input with a triangle, this implies that this is a flip-flop. If the triangle is with a bubble, then it is a negative edge, a triggered flip-flop, whether it is a D flip-flop or other types of flip-flops that we will see shortly. Okay, so this circuit basically is another way to construct a D flip-flop. It has advantages when compared to the master-slave, but I will not go into such details. We need only to know how to use these storage elements in the latches, the clock latches, and the flip-flops. And usually we will work with the block diagram of these storage elements. Okay? Now, in terms of flip-flops, there are other types of flip-flops, not only the D flip-flop. Now, the D flip-flop, basically, we said it is a storage element. A Q is affected by D at the edge. And what is the relation between Q and D at the edge? Basically, Q equals D, or we said the new value is basically the value that we see at D when the edge arrives. Very straightforward. Now, there are other flip-flops, which are basically edge-triggered storage elements, and however, they differ in the number of inputs and the relation between the inputs and the stored value. So basically here we have another type of flip-flop, which is called the JK flip-flop. It is constructed using D flip-flop, and however, it has two inputs, J and K. And J basically is the input that we can use to set the stored value, while K is basically the input that we use to reset the stored value. So this is kind of S and R. JK, it implies that this kind of is S and R. So we have now two inputs for JK, the JK flip-flop. Later, when we talk about the analysis of sequential circuits, you will be able to analyze this circuit and see how this circuit is behaves. Okay, so what we are concerned for the time being is the block diagram for the JK flip-flop. Now this is a positive edge triggered flip-flop. It has two inputs, J and K, that are used to control the stored value when there is a rising edge. When there is a rising edge. So this is a positive edge triggered flip-flop. And we will see shortly what is the relation between J, K, and the Q. How do the JK inputs affect the stored value when there is a rising edge on the flip-flop? Okay. However, we may have the flip-flop be negative edge triggered if there is a bubble here. So this flip-flop is enabled when there is a falling edge. So we should be familiar with this convention. Bubble at the clock input implies negative edge triggered, while if there is no bubble, then it is positive edge triggered. Another type of flip-flops is the T flip-flop, and it can be either constructed from a JK flip-flop or from a D flip-flop, as seen here. And later, as I said, we will see how we can design such a flip-flop using a JK flip-flop or a D flip-flop. So basically, this is another type of flip-flop, and this is the block diagram of it. It has one input, it has the stored value, it has the clock, and this is a positive edge-triggered T flip-flop. In other words, again, this flip-flop allows T to affect Q only when there is a rising edge on this input. When this input changes from 0 to 1, it allows T to affect Q in a certain way. There is some relation between Q and T. The most straightforward flip-flop was this, the D flip-flop, where Q is simply D at the rising edge. For J and K flip-flop and T flip-flop, the relation is different, as we will see here. So for the D flip-flop, this is the D flip-flop. Basically, the relation between the next value or the new value and D is the same. D is 0, then Q of T plus 1 is 0. D is 1, then Q of T plus 1 is 1. However, this is not always valid. It is only valid when there is a rising edge, when there is a rising edge on the clock input. That's why this is a positive edge-triggered flip-flop. So this is very important. This table, which we call the characteristic table, this is very important. This terminology, this is the characteristic. Okay. This is the characteristic table of the D flip-flop. Characteristic implies that it characterizes the flip-flop. How does this flip-flop work? How does it operate? In other words, what is the relation between the new value that will appear at the rising edge based on the value of the input? In this case, it is D. So either in this type of flip-flop, we have two operations, either reset or set only. So basically, always I say it, Q plus or Q of T plus 1 is basically D. Q follows D. Q is the same as the D input. Q is the same as the D input. How about other types of flip-flops? For example, the JK flip-flop. This is the characteristic table of the JK flip-flop. Basically, this table tells us what is the new value based on the value of J and K when there is a rising edge on the clock input. So here we have 4 different types of operations for this flip-flop. We can hold the value, we can reset the value, we can set the value, we can toggle the value or complement the value. So in this type of flip-flop, this is the flip-flop that has the 4 different kind of operations that we said last time. Either you can hold, you can set, you can reset, and you can complement or toggle. Okay. However, these operations or the J and K inputs are only allowed to change the stored value at where? At the edge, whether it is a rising edge or a falling edge. So these tables are very important. The characteristic tables are very important. We will use them in the second part of this chapter to analyze sequential circuits. Given a sequential circuit, we want to see what does this circuit do. So we will use these tables for the analysis part when we analyze sequential circuit. For the last type of the flip-flops, which is the T flip-flop, this is the characteristic table, or the table that characterizes the operation of the flip-flop, and it is very simple. Basically, two operations are supported. When T is 0, the new value is basically the old value. So this is a no change or a hold operation. When T is 1, the new value is basically the complement of the old value, which is a toggle operation. And this is only allowed at the rising edge because this is a positive edge triggered. These are positive edge triggered flip-flops. These are positive edge triggered flip-flops. So we need to remember these characteristic tables. We need to know the graphical symbols, and we need to understand the operation of these flip-flops. How do they behave? Basically, they are edge triggered. They are only activated at the edge. So we don't need to look at the inputs at any instant of time except this instant of time, which is the rising edge or the falling edge. Okay, what's the time? Okay, we have a few minutes. So here it is the same slide, but we have here the negative edge triggered. These have to be aligned better, but nothing different here. It is the same characteristic tables, but the trigger is different, which is a falling edge, Okay, so here we have, let's look at these examples before we go to see how these flip-flops work and to see how basically these flip-flops are easier to analyze, Here we have here an example, which is for a T flip-flop. So we have a T flip-flop here. So, and the clock is something like this. It's changing like this. So since this is a flip-flop, so we don't need to look at the clock for all the times. We only look at the rising edge because this is a positive edge triggered flip-flop. So if T now, so as I said, we need to look at the edges. So at this edge, we look at the value of T. What is the value of T? And reflect that on Q based on the characteristic table. So at this instant of time, what is T? T is 0. And what does T0 implies? Implies that the new value is basically the old value, or there is no change. And what is the old value of Q? What is the value at this instant of time? It is 0. So what happened to this value after this edge? The value after the edge will be the same as the value before the edge because T at the edge is basically 0. So what will happen here? T is 0, so Q will be affected such that there is no change. So the Q will stay the same for this whole period. Because why? There are no edges in this during this period of time. We can only change the stored value at the edge. So at this edge, there is an edge. So if we assume that T is changing like this, so what is the value of T at the edge, at this edge? It is 1, and when T is 1, what is the new value inside the flip-flop? It is the complement for the value that was before the edge. What is the value before the edge? It is 0. So the new value after the edge is toggle. So the 0 becomes 1 after the edge. So this is the idea. I did not need to monitor the clock for the whole time. I only needed to look at this instant and this instant, read the inputs, and reflect that on Q based on the characteristic table, based on the characteristic table. So this is much easier to work with instead of looking at T during some time or looking at T for at all time. Okay? Okay. Any question? Okay, so I have posted these slides on e-learning. They were initially, they were what? Originally, they were 60 slides. Now we have about 100 slides. I modified the slides so that we have more details, we have more examples. Don't panic that they were 60 slides and now they are 100, because this is usually the material that I cover in class, physically in a class. I put too many examples on the board usually. So I tried to put these examples on the slides so that we have better understanding. Here we have animations and all that stuff. So for this topic specifically, it is very beneficial to use the slides. All right. Any question? Okay, let me take these questions.